a neural network can approximate any continuous function. Today we'll see exactly why and what that really means. Let's start with a concrete example. Here's a continuous function, smooth, no jumps, defined on a bounded interval. Maybe it's a sine wave, maybe it's something more complicated. The Universal Approximation Theorem says, give me any tolerance epsilon, and I can build a one-hidden layer network that stays within epsilon of this curve everywhere. Epsilon could be 0.1, 0.01, 0.001, doesn't matter. For any epsilon, there exists a network that gets within epsilon. That's a strong claim. Let's see why it's true. The intuition starts with step functions. Imagine approximating this curve with a staircase's flat steps at different heights. It's crude, but it's a start. If I make the steps smaller and more numerous, the staircase gets closer to the curve. In the limit, infinitely many infinitely small steps would match the curve exactly. But we can't have infinitely many neurons. So we need a better building block. A single neuron with a sigmoid activation is like a smooth step. It transitions gradually from 0 to 1. Stack multiple sigmoid neurons with different weights and biases, and you get a sum of smooth bumps. Each bump can be positioned and scaled. With enough bumps, you can approximate any continuous function. This is the classical proof of the Universal Approximation Theorem, using sigmoid activations. But modern networks use ReLU. Let's see how ReLU works. ReLU is max of 0 and a linear function, max of 0 and w times x plus b. Graphically, it's a hinge. Flat at 0 for x less than minus b over w, then a line with slope w. Each ReLU unit is one hinge. On its own, it's not very expressive. But combine multiple ReLU units, and something interesting happens. Two hinges can create a single line segment. Let me show you. Take two ReLU units. ReLU 1, max of 0, x minus 1. ReLU 2, max of 0, x minus 3. Now compute ReLU 1 minus ReLU 2. For x less than 1, both are 0, so the result is 0. For x between 1 and 3, ReLU 1 is x minus 1, ReLU 2 is 0, so the result is x minus 1, a line segment with slope 1. For x greater than 3, ReLU 1 is x minus 1, ReLU 2 is x minus 3, so the result is 2, flat again. We've created a single sloped segment between x equals 1 and x equals 3, flat everywhere else. This is the building block. Now let's approximate our target curve with three line segments. Segment 1 from x equals 0 to 2, segment 2 from 2 to 4, segment 3 from 4 to 6. Each segment has a slope chosen to roughly match the curve. The approximation is coarse. There's visible error, gaps between the curve and the piecewise linear approximation. But it's a start. We've used 6 ReLU units, 2 per segment, to create 3 segments. Add more segments. 10 segments instead of 3. Each segment is narrower, and the slopes are adjusted to better match the local slope of the curve. The approximation is much tighter. The error, the maximum distance between the curve and the approximation, has shrunk. We've used 20 ReLU units to create 10 segments. The pattern is clear: more neurons, more segments, better approximation. Keep going. 50 segments. The piecewise linear approximation is now so dense that the error is barely visible. The curve and the approximation are almost indistinguishable. 100 ReLU units, 50 segments, and we're within a tiny epsilon of the target function everywhere. This is the Universal Approximation Theorem in action. For any epsilon, there's a width, a number of neurons, that gets you within epsilon. The theorem says that width exists. The same idea works in higher dimensions. Here's a two-dimensional surface, a saddle, a wave, something smooth. A single hidden layer network can tile this surface with piecewise linear patches. Each patch is a flat triangle or polygon. With a coarse tiling, the approximation is rough. Refine the tiling, more neurons, smaller patches, and the approximation gets smoother. In the limit, you can approximate any continuous surface to arbitrary precision. The theorem extends to any dimension. But there's a catch. The width you need grows with the dimension and shrinks with epsilon. In one dimension, you might need 1 over epsilon neurons. For epsilon equals 0.01, that's 100 neurons. In 2 dimensions, you need 1 over epsilon squared. That's 10,000 neurons. In 10 dimensions, you need 1 over epsilon to the 10th power. For epsilon equals 0.01, that's 10 to the 20th neurons. More neurons than atoms in the observable universe. The theorem says it's possible. It doesn't say it's practical. This is the curse of dimensionality. The theorem is an existence result. It says a network exists that can approximate your function. It doesn't tell you how to find that network. It doesn't give you the weights. It doesn't tell you whether gradient descent will converge to those weights. Training is a separate problem. You might get stuck in a local minimum. You might need careful initialization, learning rate tuning, regularization. The theorem guarantees expressivity. It doesn't guarantee trainability. Here's a dataset, 10 noisy points sampled from a parabola. A very wide network can fit all 10 points perfectly. 0 training error. Perfect approximation of the training data. But look at the learned function. It's wiggly. It passes through every noisy point, including the noise. On new test points from the true parabola, the error is high. The network memorized the training data but didn't learn the underlying pattern. This is overfitting. Approximation power, the ability to fit training data, does not imply generalization, the ability to predict test data. The Universal Approximation Theorem guarantees the first. It says nothing about the second. So if one hidden layer is enough in theory, why do we use deep networks? Because depth provides efficiency and structure. Certain functions can be represented exponentially more compactly with depth. Imagine a function that composes simple operations. First apply function g, then apply function h to the result. A deep network can dedicate layer 1 to g and layer 2 to h. A shallow network has to represent the composition g of h directly, which might require exponentially many neurons. Depth also provides hierarchical feature learning. Layer 1 learns edges. Layer 2 learns textures. Layer 3 learns object parts. Layer 4 learns objects. This compositional structure is why deep networks work in practice, even though shallow networks are universal in theory. The Universal Approximation Theorem tells us neural networks are expressive enough. That's important. It means we're not fundamentally limited by the model class. But the theorem is not a practical guide. It doesn't tell us how wide to make the network. It doesn't tell us how to train it. It doesn't tell us how to make it generalize. Those are engineering problems, not theoretical guarantees. The theorem is a license to hope. It says, in principle, a network can represent what you want. But turning that principle into practice requires architecture design, optimization algorithms, regularization, data augmentation, and a lot of empirical trial and error. Theory gives us confidence. Practice gives us results.